So we're given here a 15 kilogram stone sliding down a snow-covered hill that is 20 meters high and 15 meters wide, leaving point A at the top with a speed of 11 meters per second. There is no friction on the hill between points A and B at the bottom of the hill, but there is friction on the level ground at the bottom of the hill between B and the wall. So we're given that from A all the way to B, this is frictionless. And then we have from B till this wall to which a spring is attached, we have friction. The mass is given to be 15 kilograms. And at the top, the speed right here is 11 meters per second. After entering the rough horizontal region, the stone travels 100 meters and then runs into a very long light spring with a force constant of 2.5 newtons per meter. So we're given that the distance here is 100 meters, after which the stone can compress this spring. The coefficients of kinetic and static friction are given for the surface on which we have friction. The first question, what is the speed of the stone when it reaches point B? So we're interested in the speed here. Trivially, we know that between A and B we don't have any friction, so we can set the mechanical energy to be constant. So the energy at A is equal to the energy at B. And we know that at A we have kinetic energy and potential energy, while at B we will only have kinetic energy, because we're going to take this as our reference for gravitational potential energy. So what remains is we substitute the expressions. So remember that this is what we want, the speed at B. So we can rearrange our equation to find this speed. And we get this expression for the speed at B. All the terms here, we have them, so we can just substitute the values. So we're given that the mass is 15 kilograms. However, this mass, we can observe that it will cancel out. So I'm not going to substitute it in my expression. The speed at A is 11 meters per second. H is 9.8. And the height is 20 meters at point A. So if we solve this, we get a speed of 22.6 meters per second at point B. In part B, how far will the stone compress the spring? So we want to know how far the stone is going to compress the spring. So remember that after covering 100 meters on the rough surface, the stone will compress this spring, and we want to find the distance x by which this spring will be compressed. So since this is a surface with friction, then the mechanical energy will not be the same. We know, however, that the change in the mechanical energy will be equal to the lost energy, and this is equal to the work done by the friction. So we can write in part B that the energy at B will be equal to the energy at the point of maximum compression, which I will name as C, plus the energy lost due to friction, which is equal to F times D. This is the work done by the friction. So at C, we can look at what kind of energy we have. This is point C, this is where we have our maximum compression. So at point C, since this is the point of maximum compression, we know that the speed will be momentarily zero since we are at maximum compression. And we will have an elastic potential energy instead, which is equal to half kx squared, where x is the maximum compression, and this is actually what we want. At B, however, um, we have kinetic energy only. We don't have any elastic potential energy since we're not in contact with the spring yet, and we don't have any potential gravitational potential energy because we are at the reference level. So the energy at P is just half mvb squared. We found Vb in the previous part. The energy at C will be just half kx squared. The friction can be found by saying it's equal to mu times the normal. Now, the normal is equal to the weight here, because if we check the vertical forces, we only have the weight and the normal. So this will be mu k times mg. Now the distance covered over which we have friction, this is important because from B to C we have friction, and then from B to C the distance is 100 plus x, which is the compression of the spring, because the stone covers 100 meters and then the compression starts for a distance of x meters over which we have friction as well. So this distance here is going to be 100 plus x, where x is the compression. So you will notice that we have two terms containing the compression in our equation. What we will do next is that we will substitute the values and then solve for x. So we know that the mass is 15 kilograms. V at B was found to be 22.6. K is 2.5. X is what we want. Mu k is 0.2, m is 15 again. This is 9.8 into 100 plus x. We will actually obtain a quadratic equation when we solve and simplify this equation. We will get an expression in terms of x squared and x, and we will have to solve this equation in order to find x. So if we solve this equation, you can use your calculators to find the solutions. You will get two solutions. One of them is negative, the other is positive, and of course we take the positive value. We will find that the compression is equal to 17.4 meters. We still have part C, in which we are asked, will the stone move again after it has been stopped by the spring? So we have reached point C where we have a momentarily stop. However, the spring is exerting a restoring force. It will try to push the stone back in the opposite direction. Will the stone move? So to know if the stone moves, we think of the forces that we have. If the restoring force exerted by the spring can overcome the friction, the static friction in this situation, since we have reached a momentarily stop, then yes, there will be motion. Of course, here the spring will have to overcome the maximum value of the static friction, because we know that the static friction increases as we increase the applied force until we have this maximum at which the static friction cannot balance the exerted force anymore, and then the forces are unbalanced, and then the stone will move. So to find the static friction, we know this is going to be mu s times n, which is mu s times mg. So this is 0.8 times 15 times 9.8. If we calculate this, we get a value of 117.6 newtons. While if we look for the other force, which is the one exerted by the spring, this is going to be equal to k times x, with k being 2.5 and x is 17.4 meters as we found in the previous part. So if we calculate this, we will get 43.8 newtons. Obviously, the maximum value of the static friction is much more than the exerted force, so the static friction will be able to balance the spring force. which means that the stone will not move again because the friction is still strong enough to balance the restoring force exerted by the spring.